Well, hello and welcome to our third Thursday webinar. I am Tom Sandri, and today we are going to be talking about Time Domain Reflectometry, technology review, and applications. So, let's get started. Now, a Time Domain Reflectometer, or TDR, measures reflections along a cable. In order to measure those reflections, the TDR will transmit an incident signal into the cable and watch for reflections. If the cable is of uniform impedance and it is properly terminated, then there will be no reflections and the remaining incident signal will be absorbed at the far end by the termination. Instead, if there are impedance variations, then some of the incident signal will be reflected back to the source. As we can see, the time domain reflectometer is very similar in principle to conventional line-of-sight radar, where in line-of-sight radar, as we're aware, a high-frequency pulse is launched or transmitted out. As this pulse propagates, it travels and travels until it encounters a physical object, for instance, an aircraft. The pulse reflects from the aircraft and returns back to the source. This is very similar in principle to the way the time domain reflectometer is operating. The TDR analysis begins with the propagation of a step or impulse of energy into a system and the subsequent observation of the energy reflected by the system. By analyzing the magnitude, duration, and shape of the reflected waveform, the nature of the impedance variation in the transmission system can be determined. If a pure resistive load is placed on the output of the reflectometer and a step signal is applied, a step signal is observed on the display, and its height is a function of the resistance. The magnitude of the step produced by the resistive load may be expressed as a fraction of the input signal as given by the equation. Rho, or in this case reflection coefficient, would equal the resistance of the load minus the characteristic impedance of the transmission line divided by the resistive load plus the characteristic impedance of the transmission line. Now, two side-by-side conductors that are separated by an insulator, as in a cable, have a characteristic impedance between them. If the distance between the conductors does not change, this impedance does not change. If the distance between the conductors increases, the impedance goes up. If the distance between the conductors decreases, the impedance goes down. Time domain reflectometers, or TDRs, use simple transmission line theory and pulse reflection principles to detect these impedance changes encountered along a cable. The TDR transmits high-frequency electrical pulses that travel through the cable until a change in characteristic impedance is encountered. Depending on the nature of the impedance change, either all of the transmitted pulse or a part of the transmitted pulse will reflect back to the time domain reflectometer. As we see in this illustration. Now, a change in characteristic impedance will cause one of two types of reflections, either a positive reflection or a negative reflection. Positive reflections are caused by increases in impedance. This will occur if the longitudinal resistance were to increase or if the conductors go farther apart, causing an inductive change. Negative reflections are caused by decreases in impedance. This will occur if the conductance or capacitance change as the conductors get closer together, causing a capacitive change and lowering of impedance. The reflections are translated by the time domain reflectometer into traces, which can be interpreted to indicate certain events, such as open circuits, short circuits, splices, etc., in the cable circuit. All traces follow the two basic rules of impedance changes. Now, here we see an example of a splice. When the TDR pulse enters the splice, it will initially see an inductive change, causing a small positive reflection. Again, it's a subtle change, so not all of the transmitted pulse reflects back, only a small portion of it. It is an inductive change because as we enter into the splice, we see that the natural separation of the conductor and metallic shield increases. As the TDR pulse travels through and exits the splice, we see a change in capacitance causing a small negative reflection as the TDR pulse leaves the splice. The capacitive change is being caused by the metallic shield and the conductor now coming back to their natural characteristic distance. So a splice pattern or splice trace is really just two reflections occurring back to back. The inductive change entering into the splice, followed by the capacitive change exiting the splice. Now, reading a time domain reflectometer signature is like reading a map. But before we read a map, we need to learn what the symbols represent. Now, before reading a time domain reflectometer trace, we must also learn what the reflective patterns represent. And here we show a small sampling. For instance, an open circuit would be represented on the TDR trace as a large positive reflection. Again, an open circuit would be an infinite increase to the longitudinal resistance along the transmission line. In an open circuit, all of the incident energy must now stop. It cannot go any farther, and it will reflect back in phase to the TDR. In the case of a short circuit, impedance being 0, or the insulation resistance or conductance basically being at a 0 resistance, all of the TDR energy reflects back from the short circuit 180 degrees out of phase with the incident energy, or in the form of a negative reflection. Again, the amplitude or depth of the reflection indicate the severity of the event. As we just covered, a splice or a joint in a cabling system is actually two reflections, the inductive change going into the splice or joint, followed by the capacitive change coming out. Now, a well-built splice will typically be somewhat symmetrical. The amount of inductive change and the amount of capacitive change will be somewhat symmetrical. Now, in the case of a wet splice where we have water ingress into the splice, we would see an imbalance to this symmetry. We would see the inductive change going into the splice, the capacitive change coming out of the splice, but we would also see the influence of the moisture further changing the capacitance at the splice. So, in essence, the splice pattern now becomes bottom heavy, showing more of a negative tail, indicating the possibility of water ingress. In a high resistance splice, for instance, where the conductor connector may not be crimped properly, or there may be corrosion building on the metallic shield, adding to the longitudinal resistance, we again would see the positive reflection for the inductive change going into the splice, but we would also see an increase to the metallic resistance either caused by the pore crimp or by corrosion, adding resistance to the longitudinal resistance of the metal. And the pattern would be a top-heavy S or a top-heavy splice pattern. Now, the time domain reflectometer pulses can also go through most transformers. A transformer will be very similar in nature to a splice. Feeding in, the TDR would see an inductive change followed by a capacitive change as it leaves the transformer. Now, note, the TDR pulse does not enter the core or the windings. It merely travels through the transformer connection. Now, also, if we were to have a T-tap or a Y or branch connection, what the TDR would see here is the large capacitive change due to the branch of cable or the section of cable that is being tapped into the main run. Now, knowing that these events are in the cable is beneficial, but to be helpful, we need to know where they are in the cable. Now, we discussed that a TDR sends pulses along the cable that are reflected when they encounter a change in impedance. The TDR times how long it takes for the transmitted pulse to travel along the cable and the reflections to get back to the unit. If it knows how long the pulse has been gone and how long it has been traveling, it can determine distance. TDRs are like an arithmetic word problem that asks, if you leave Dallas and travel for 2.5 hours at 50 miles per hour, how far have you gone? Because the TDR knows how long the pulses have been gone, if we could tell it how fast these pulses and the reflections travel along the cable, it would be able to calculate the distance from the TDR to the impedance changes. And we can do this. But to complicate it, the TDR's pulses travel at different speeds in different types of cable. The transmitted pulses travel at different velocities on different cables, much like a ball travels at different velocities through liquids with different viscosities. The velocity of propagation changes according to the following factors: the impedance of the cable. The dielectric materials that are being used will have an influence on the propagation or the velocity, such as, are we traveling through cross-linked polyethylene, PVC, ethylene propylene rubber or EPR, or possibly paper-insulated lead-covered or PILC cable. Age of the cable will also influence the velocity of propagation, as will temperature and possible moisture content or moisture ingress inside the cable. With telecommunication cables such as twisted pair, the wire position inside the cable will have an influence on the velocity of propagation. And also cable manufacturer. For instance, composition of insulation material and any additives that are being used will all have influences or be factors in the velocity of propagation. Now, fortunately, we can tell the TDR how fast the pulses and the reflections travel in various cables. This speed is usually stated as a ratio of the speed of the pulse in the cable divided by the speed of light in a vacuum. This ratio is called the velocity of propagation. If the velocity of propagation, for example, is 0.50, the speed of the pulse is 50% of the speed of light in a vacuum, or 0.5 times 186,000 miles per second. Now, here we see some velocity of propagations for various cable types. You'll note that many of the power cables are in the area of 50 to possibly 60% the speed of light. When we're looking at telecommunication cables, we typically are looking at velocity propagations in the 60s to 70% speed of light. In twisted pair cables, again, in the areas of 60 to 70% the speed of light. Now, if velocity is not known, the velocity of a cable can easily be determined by connecting onto a sample cable of known length. If we can see the length markings or measure it to get the length of a section of cable, we can work backwards with the TDR and, in essence, calculate the velocity of propagation. Simply, if we know the true length of a cable and the TDR knows the time the pulses and its reflections were gone, the speed or velocity can then be calculated. The TDR now has enough information to calculate where the event is, like our trip from Dallas. It knows how long the pulses and its reflections traveled, and it knows how fast the pulse was going. The TDR merely must do the arithmetic. Now, in the example that we show on the screen, if we identify the end termination of the cable, here we see it terminated as an open, we place our display marker at that event. If we know the true length, we can then increase or decrease the velocity of propagation until the TDR calculates and displays the proper length. If we are measuring too short of a length, we would increase the velocity of propagation. If we are measuring too much length, we would decrease the velocity of propagation. Now, if neither the velocity or length of the cable is known, an accurate locate can be accomplished by simply measuring the distance to the fault from both ends of the cable. The trick is, whatever velocity we use the same velocity while measuring from the near end and from the far end. If an error exists in the velocity setting, the TDR will either overmeasure or it will undermeasure from both ends of the cable. The fault or event that we're looking for will be between the two measurements. If the two measurements fall substantially short of one another, we can increase the velocity, retake our measurements, bringing the markers in closer. If we overshot the event from both ends, we can decrease the velocity, reshoot the line, and bring the markers in closer. Now let's talk a little bit about pulse width. Does it matter if the event that we are trying to find is very close to the TDR or very far away from the TDR? Well, it sure does. We can look along the entire distance of a very long cable by varying the power, the width, of the pulse that the TDR sends out. This is the amount of time that the transmitter is turned on. We set the pulse width. TDRs have varying pulse width settings, and modern units, while allowing the operator to vary the pulse width, they will automatically set the proper pulse width to the best display for the first event. The larger the pulse width, the more energy, and therefore the farther the signal will travel on a given cable. A TDR's distance range is determined by how far the transmitted pulse will travel while still having a detectable reflection return to the TDR. So why don't we just send the most powerful pulse at all times? The width of the transmitted pulse will affect the TDR's ability to identify reflections. It's a bit like walking in from the dark and turning on a bright light. The power of the light overpowers our receivers, our eyes, and blinds us for a minute. Our eyes adjust by reducing the amount of light that enters our receivers. Now, the TDR's receivers don't do this, so lower powered pulses for close-in events have to be set. The width of the pulse is sometimes referred to as the dead zone, the distance that the TDR is blind. Now, the table shown is a table that relates the typical dead zone at launch to the pulse width in communications coax cable. As we can see as a few examples, a 2 nanosecond pulse width would result in a 3-foot dead zone, or 3-foot blind area. A 100 nanosecond pulse width would result in a 55-foot dead zone. Now, we not only have to worry about blind spots at launch right next to the TDR, but the reflections of events also have blind spots, the size of which are related to the pulse width. The second of two closely spaced reflections may become masked by the dead zone of the first event or the first reflection. Now, as seen in the following screen captures, a wide measurement pulse shows all reflections clearly and on a large scale. But if a higher level of accuracy is required, then the pulse width must be reduced. Only then can smaller changes be seen clearly. Now, another item I would like to point out is with a wider pulse width, we have more energy traveling into the cable and therefore more potential energy being reflected back. When we reduce the pulse width, we have less energy going into the cable. We pick up spatial resolution by reducing the dead zone, but we will need to perform amplification because the signal will attenuate much faster, being less energy being transmitted into the circuit. Now, typical pulse widths that are used in time domain reflectometers. 1 nanosecond to 3 microsecond. These are pulse widths that are typical in high-resolution reflectometers that are optimized for communication cables. 35 nanoseconds out to about 5 microseconds. These pulse widths are typically used in reflectometers that are used on electrical power cables. 50 nanoseconds to 20 microseconds. These pulse widths are used in special models that are designed for long cables, for instance, undersea cables. Cable insulation and dispersion. The cable cross-section and length both lead to changes in the amplitude and form of the sent pulse in the cable. The insulation leads to a reflected signal becoming smaller as the distance increases. The insulation is shown by a red line in the diagram. Dispersion is another factor that influences the pulse image. As high signal frequencies are absorbed more than low frequencies, far-off pulses appear much wider than nearer ones. Due to the combination of insulation and dispersion, these signals can only be determined with some difficulty. Now, let's take theory into practice. First, a time domain reflectometer, or TDR, cannot work on a single conductor. The TDR relies on the impedance model of two conductors in parallel with one another. TDR pulses do not travel down the conductor and return on the neutral. TDR pulses travel down the conductors and reflect back on the conductors. Let's think of the TDR pulse as a train and the cable as train tracks. The train requires two tracks or rails in order to function. The TDR pulse requires two conductors traveling in parallel with one another. If one rail is missing, the train needs to stop. If one conductor becomes open, the TDR pulse cannot travel any further. If a rail is missing, the train may need to return to the station, and it will take the same path, but simply traveling in reverse or backwards. If a conductor is open, the TDR pulse cannot continue, and it will reflect back to the source along the same transmission line, except traveling backwards or returning to the source. All right, let's get a little practice time in. So, we see two TDR traces, blue and red, phase A and phase B. What are these TDR signatures telling us? Go on and take some time, and in your questions function, go ahead and type in what you believe you are seeing on the blue trace and type in what you are seeing on the red trace. Take a few moments to type in your answers. Okay, I see some of you have entered in answers. Well, what we are seeing in the blue waveform or trace, we see the launch pulse going into the circuit, and we see the wiggle or sine wave pattern. Looking at our TDR legend, we see that this is a splice, and we have a repeat of this pattern. So we have 1, 2, 3 splices, followed by a large upward reflection, which most likely is the open circuit or the termination at the end of the cable run. We see a repeat of this on the red waveform, the incident energy going in, 2 splices, and the third splice here we see is a different pattern. We see a large negative reflection, which would indicate that there is a short circuit or the splice has become a short circuit and a fault. Now let's talk some applications. Let's first look at the application of TDRs being used in signal and control cables. Requiring low amounts of energy, TDRs are a safe tool for operators in a variety of applications. In difficult-to-reach locations, a TDR is a particularly valuable tool. Now, after the Deepwater Horizon oil spill back in 2010, scientists enlisted the help of robots to aid the cleanup efforts. These engineered submarines were attached to lengthy cables off the oil platforms, sometimes extending a mile deep into the ocean. When cable troubles arose, technicians used time domain reflectometers to identify cable faults and shorts from water ingress into the cables, despite the cables extending thousands of feet into the ocean. And here we see 2 screen captures where, for instance, measurement to an open conductor or measurement to a short circuit in these signaling control cables. Now, for telephone and cable TV applications, water can seep through the conductors of a twisted pair cable at multiple ingress points along the insulation. In these situations, testing the cable from both ends and recording the distance to fault will give the lineman an accurate illustration of the severity of the water issue or confirm that the initially spotted abnormality is correct. For example, if the cable under test is 500 feet long and it reads 100 feet from one end and 200 feet from the other, the operator is looking at around 200 feet of overall soaked or water ingressed cable. When installing a new cellular site, the Time Domain Reflectometer is particularly useful for ensuring that specific cables are connected to the proper antennas. Now again, we show a couple screen captures. In our first screen capture, we show the pattern indicating water damage or water ingress in the cable. Notice that predominantly these are negative reflections since water will alter or change the capacitive property of the cable. They are random in nature because water is not evenly distributed as it saturates into the insulation. But we can measure to this event and determine how much of the cable is affected by the water ingress. In our second captured waveform, we show what we call a line tap or a bridge circuit. Here is where a cable actually taps into the main feeder, forming a branch. Again, when we tap into the main feeder, we see a capacitive change or the added capacitive load of the branch circuit that is tapping into the main line. So, let's take a look at a practice time again. Let's say we have two branch circuits, one shown in example 1 and in example 2. We have a main feed and a tap or branch feeding into the client or through the resident. Now, this could be twisted pair communication cables. This could be cable TV cables. This could be low voltage electrical power cables. Now, the waveform generated, for example, from example 1, would show multiple locations of impedance mismatches or events that are occurring along the transmission path. Here, at point A, we would see the incident energy or the pulse entering into the circuit from the time domain reflectometer. The first point of impedance mismatch occurs at the tap, where we see a capacitive change taking place resulting from the capacitive load of the branch circuit. So we see a negative reflection. Now, at this point, the TDR pulse is going to split. Part of the TDR pulse is going to continue traveling along the main feed, while part of the pulse breaks loose and travels along the branch circuit. The events that we see next are going to be based on time of flight. For example, in example 1, we see the reflection from point C, the client, because the branch is shorter in physical length than the main feed going to the end termination. Therefore, the pulse that travels down the branch reaches the impedance mismatch first and reflects back to the TDR. Meanwhile, the pulse that went through the branch and continued along the main cable finally reaches its destination or termination at point D, and again we show it represented as a high impedance termination or possibly an open circuit. Now, let's take a look at example 2. We have a very similar pattern. Once again, we have our launch pulse going into the circuit. The first event or impedance mismatch that we come to is the branch circuit at point B, but now the TDR energy that travels to the end of the cable has the shorter distance in this example, so we see the end of the main line at point C, and then finally the end of the branch circuit or the client or resident. Now let's take this one step farther. Let's go back to example 1. We've identified all of the events that occur in this trace in a normal operating circuit. So once again, we have the launch pulse. We have the first event being the tap. As the TDR pulse is split, we see the termination at the client or home, and we see the termination on the main feeder. Now, let's say that a fault were to occur in this circuit. So we now capture the pattern of the faulted circuit. What is this new trace telling us? Go ahead, take a moment, review the trace, and type your answer into the question function. What do you think we are seeing in this new trace? Well, okay, let's break this down. We still see the incident energy leaving the TDR and entering into the circuit at point A. Now, the very first event that is captured on both the good cable and faulted cable, we see the capacitive change of the tap point or the branch. That has not changed in either waveform or trace. Now, on the good cable, the green trace, we see the presence of the termination at the house. However, on the blue or the faulted trace, we no longer see the upward reflection terminating at the home. Instead, we see a large impedance increase very close to the tap position or the branch connection point. This would imply that we have possibly an increased impedance or open circuit. Since we're not seeing to the house any longer, we can conclude that we have an open circuit in the branch feeding into the client or to the house. Now notice along the main feed, from the branch to the termination of the main feed, we do not see any changes, and we can still see the end termination event of the main feed. So again, our conclusion would be we have a fault, an increased impedance or open circuit on the branch feeding off of the tap going to the resident or home. All right, another application for TDRs is in the mining industry. Because of the risk of explosion, most countries do not allow TDRs down mines. However, as the mine deepens, shafts are dug from the surface and umbilical cables are dropped down. These cables carry power for the tools and telecommunication needs. Due to the distances involved, these cables, especially those used for telecommunications, become stretched and are likely to fail. Simple numeric or graphical TDRs are used to test cable integrity and to locate failures such as opens or short circuits. Now, here in the screen capture, we show the representation of a stretched cable conductor. It increases the longitudinal resistance of the metallic wiring, causing an increase in impedance or a positive reflection. Now here we still have continuity. We have added resistance due to the stretching of the conductor, and we are still able to see the end termination or the end of the cable. Now let's also talk about applications in the electrical world. Illegal taps are a huge problem for many electrical companies throughout the world because millions of dollars are lost due to theft of service. An illegal tap occurs when an individual connects to the power cable before it reaches the meter. When a customer connects before the meter, they bypass the meter that measures power consumption. In the United States and other similar networks, power is distributed using high voltage lines to the neighborhood. The high voltage is reduced by a step-down transformer near the customer's home. The smaller low voltage is 110 volts that runs most of our appliances. In most cases, homes receive two phases of 110 volts in order to power larger appliances that may run on 220 volts. These two phases are run with a neutral. Normally, the drop line will run directly from the transformer to the house. However, the power company may run a feeder cable of 110 volts to connect a strip of houses or businesses. Either way, the cable runs to a meter box that registers power usage for the billing process. After the meter, the cable runs to a breaker box and then is distributed throughout the subscriber's home or office. Now, here in our screen capture, we see an illegal tap where this individual branched onto the cable feeding to the meter, but tapped into it prior to it reaching the meter. Therefore, all of the electricity going down the tap is not being registered on the meter. Let's continue looking at low voltage electrical applications. Now, the best methods for fault locating on a low voltage circuit involves a good versus bad type of comparison. A healthy TDR trace produced by the complex network shows many reflections caused by the service connection, taps, and the ends of these cables. Now, even a gross fault down the network would be masked by the other features of the network. In many cases, comparisons and differential techniques are the only options. Well, and let's face it, the comparisons and differential techniques makes the interpretation of the TDR signatures so much easier. Here we show a couple examples where we show, for instance, a good phase laying on top of the trace generated by a bad phase. Here we would see on the good phase a splice pattern. On the bad phase, we would see a short circuit replacing the pattern of the splice. Our conclusion, on the bad phase, we have a short circuit at the splice location. Now, here we show open conductor near the end of a termination. So in this one, on the good waveform or good trace, we would see looks like a little bit of a high resistance splice, and we would see the end termination. On the faulted line, we would see the high resistive splice, but we would see an open circuit before reaching the end of the cable, so we can conclude that there is an open conductor before we reach the termination. All right, it's practice time again. Get ready to type those answers into the question function. All right, here we have three conductors of a low voltage circuit. We connect between conductor 1 and conductor 2, and we get the pattern shown. We now move the test leads and connect between conductor 2 and conductor number 3, and we capture the following pattern. Finally, we now connect between conductor 3 and connector 1, and we capture the following pattern. What is the nature of the fault that we can conclude from these 3 captured traces? Take a moment and enter your answer into the question function. Well, all right. Well, let's take a look here. When we connected between conductors 1 and 2, we were able to see all the way to the end of the cable termination, here represented as an open circuit. When we connected from conductor 2 to conductor 3, we measured a large impedance change, a large increase in impedance, upward reflection, which we can conclude to be an open circuit since we can no longer see to the end of the cable run. So when connecting between conductors 2 and 3, we see an open circuit. When we connect from conductor 3 to conductor 1, we also see an open circuit at the same location. Our conclusion is that there is an open on conductor 3. We know the open is not on conductor 2 because when we looked from conductor 1 to 2, we had beautiful continuity and saw to the end termination. The open circuit only shows up when conductor 3 is part of our connection. All right, let's do another one. So, 3 conductors, what are these TDR signatures telling us? We connect between conductor 1 and conductor 2, and we see all the way to the end of the cable. We connect between conductor 2 and conductor 3, and finally, we connect between conductor 3 and conductor 1. So, observing these 3 captured waveforms for comparison, type into the question function, what is the nature of the fault that we see here? All right. Well, when we connect between conductors 1 and 2, we see all the way to the end of the cable. When we connect between conductor 2 and 3, we see all the way to the end of the cable. When we connect between conductor 3 and conductor 1, we see a large decrease in impedance, or the pattern for a short circuit, and we never see to the end of the cable. The conclusion is that we have a short circuit, or conductor 3 is shorting out to conductor 1 at this location. All right, let's now take a look at the application of time domain reflectometry applied to medium voltage electrical power cables. The arc reflection method of fault prelocating on medium voltage electrical power cables combines the use of a time domain reflectometer and a surge generator, also known as a thumper. By using an arc reflection filter, a low voltage time domain reflectometer and a high voltage surge generator can both be connected to the faulted cable, and the TDR can be looking down the cable while you're surging or thumping that cable. The filter protects the TDR from the surge generator's high voltage pulses and routes the low voltage pulses down the cable. This method utilizes the fact that when an arc is created at the fault, its resistance is reduced to a very low value, less than 200 ohms, which will reflect the TDR pulses. The arc location will appear as a downward going reflection, a short circuit, on the TDR cable trace. Now, one of the features of a time domain reflectometer is that it is a low voltage pulse that is being transmitted into the cable. Now, a certain amount of impedance change has to occur in order to create a reflected pulse that we can observe and see on the TDR trace. When we're dealing with medium voltage electrical power cables, the nature of the failure might be very high in impedance. The TDR's low energy pulse does not detect enough of an impedance change to show us the defect. By coupling the TDR with the surge generator, the process is actually taking two patterns. We first take a signature of the cable under the low voltage condition, or just the TDR pulse. Now, in many cases, if the nature of the fault is a high impedance breakdown in the insulation, the TDR pulse will travel directly past the fault point and will reflect from the isolated termination at the end. We then send in a high voltage breakdown surge into the cable along with the TDR pulses. Upon reaching the high impedance fault, the high voltage impulse breaks down the fault, causing a momentary short circuit as the fault arcs over. At that moment of time, the impedance is 0 ohms. The TDR pulse reflects off of that large impedance change, or arc, and the second trace that we capture shows us the short circuit that is caused by the arcing fault. And that is the principles of arc reflection. We utilize the low voltage technology to allow us to peer into the cable and see events. We use the high voltage surge generator to reproduce the conditions to create the fault event, reduce the impedance to 0, and capture it with the TDR pulse. All right, let's take another look, a practical look at the use of a TDR as it was applied during a diagnostic study for one of our clients. Now, the client was a refinery, and they had a 600-foot cable run that was acting as one of their feeders. Now, along the 6,000 foot, there were 15 splices, and they were spaced apart at about 400 foot. The cable actually ran underground, and then every 400 feet came up to the surface where there was a splice pad, and then would go back underground and would continue for the 6,000 feet. Now, this cable was about 27 years of service life. It was a hybrid that was consisting of both ethylene propylene rubber, but predominantly cross-linked polyethylene. They had one prior failure back in 2013. Now, one of the tests that we ran on the cable was the tan delta test. Now, if you want more information on tan delta testing, I would encourage you to go back to one of our past webinars when we did our webinars on cable diagnostics. But for the purposes of our webinar today, the tan delta test is a test that allows us to look at the condition or overall health of the insulation in the cable. Now, here we see two traces or two graphical plots of our test results. The tan delta test was ran over 4 voltages: 1/2 operating voltage phase to ground, 1 times operating phase to ground, 1.5 times, and 1.7 times. So we were basically doing a condition of the insulation and a withstand strength of the insulation. Now here, the cable was made up of 2 conductors per phase in order to handle the ampacity of the circuit. Conductor number 2 of the C phase flashed over and faulted when the voltage reached 8.7 kV. Also, notice that our tan delta values at the 1.5 times operating phase to ground, the tan delta values were 60 and greater. Now, when we look at the typical tan delta values, the standard deviation and the differential tan delta between the 1/2 operating phase to ground and the 1.5 operating phase to ground, we can determine good, monitor, or action required. So, taking a look at our test results, we see that the tan delta value, the average tan delta value, was greater than 60. Now, for the type of EPR that was being evaluated, this puts the cable in the action required category. Now, we look at the stability of the readings captured, and again, we see that we are in the action required category. And finally, when we look at the tip-up, or the measured tan delta at 1/2 U0 versus 1.5 times U0, once again, we see that we're in the action required category. This cable run does not look very healthy at this point and could be a high reliability to the client. Now, here is where we use time domain reflectometry. One, we wanted to locate the failure on the C phase conductor, and we also wanted to get an idea of what was the contamination and where was the contamination in the cable. So, the waveforms that we captured were relatively complex in nature. We do see a lot of lowering of impedance, a lot of negative reflections, although we do see some areas of longitudinal increased impedance or resistance, possibly due to corroding of neutrals and water ingress or water saturation getting into the cable. So based on the rather complicated waveform, we confirm that the large tan delta numbers or increase in the dielectric losses were being caused by both corrosion as well as water ingress. Now, when we overlaid the waveforms, notice that at 623 feet, where the cable was merely wet, we had random displays of water ingress. Again, water's not going to be evenly distributed amongst the conductors and particularly amongst the different phases. But here, all the patterns came together and merged, showing a significant lowering of impedance on all of the conductors at the 623-foot location. Now, that location took us directly underneath of railroad tracks. and it was confirmed that the fault was definitely below the railroad crossing. In essence, what had happened was over time, the weight of the cars compressing down caused the conduit to collapse, crushing the cable, causing a large capacitive change, lowering the impedance of the cable, and eventually faulting the C phase at that location. But all the conductors were suffering from the crushed conduit, complicating also moisture getting into the cable at that point. Now, when we pulled the cables out of the conduit, this is what we found. Obviously, we see significant corrosion on the ribbon shield, as well as we see that there was a tremendous amount of moisture and heat buildup, causing the outer jacket to become completely deteriorated. Now, after removing this 400-foot section of cable, we went back and retested with the tan delta. Notice now that the tan delta readings drop significantly. Prior, they were at 60 and above. Now they're down to around 50. We'd still see a little bit of a tip up on it. So the cable is not perfectly healthy at this point, but let's see how much we've improved by simply removing that 400-foot sector. Well, the tan delta had dropped, now putting us into the monitor category. We see that the stability got much better, putting us into the good category. And we see that the amount of tip-up was also reduced by removing that 400-foot bad section. And we're now into the monitor. So, what we were able to conclude was through the use of the TDR, we were able to identify the nature of the contamination. We were also able to get a distance of where the main damage had occurred. And by replacing that 400-foot section that went underneath the railroad tracks, we were able to increase the performance of the cable circuit as a whole, making it more reliable. Now, the client was very impressed with this, and the next year, when we came back out to do the annual testing, we again used the time domain reflectometer, and we again just looked at where the contamination was most abundant, and then the client used that 400-foot section as their budget for replacing in the next year. And they just slowly started to increase the reliability and longevity of their cable circuit by each year during the annual testing, monitoring how much contamination, and then using the TDR to identify what section has the most contamination in it, and then scheduling cable replacement in that 400-foot section. So, a very practical use of the time domain reflectometer. All right, in summary, the time domain reflectometer is a very versatile, low voltage device that can be used on practically any cable structure, provided there are two conductors traveling in parallel. The TDR creates a map of the cable displaying impedance changes or events that occur along the transmission path. Distances to events can be determined by knowing the travel time between the launch of the incident pulse and any reflected pulses, and knowing the speed or velocity at which the pulses are traveling. Pulse width settings determine how far pulses can travel and reflect along a cable. They also determine dead zone or ability to identify closely spaced events. TDRs come in a variety of styles optimized for various applications. We have TDRs that are, for instance, optimized possibly for communication applications, those that are optimized for electrical power, or TDRs that are optimized for special purpose, for instance, very long cables like submarine or underwater cables. Here we show some different samples of standalone TDRs that operate off of either mains power or battery operated. Also single channel handheld units. We see units that are integrated into the high voltage surge generators for the medium voltage cable application or the arc reflection technique. So there are a variety of TDR configurations depending upon the application that they are going to be used in. And that concludes our webinar today on Time Domain Reflectometry, the techniques review, technology review, and applications. As always, thank you so much for joining us on our Third Thursday webinars. We here at Protec do really enjoy seeing you guys come back month after month, and we definitely enjoy doing the research and developing these webinars for you. I hope you do find value in them. All right, without further ado, let's get to those questions and answers.